It all starts with a number. A tiny, almost invisible change. Imagine the universe had a secret code, a set of master rules that everything follows. Picture one rule changing by just 1%, not a big change. If your salary rose 1%, you might not notice. In the cosmos, 1% is not small. It is a death sentence. It is the beginning of the end. A tiny glitch, a whisper in the laws of physics, unravels everything. From the smallest atom to the largest galaxy, the cosmic tapestry comes undone. We live thinking the world is stable. The sun rises, gravity keeps our feet on the ground, water is wet. These feel permanent. What if the universe sits on a knife's edge and a slight nudge sends it into chaos? A 1% shift is that nudge, a tiny number with final consequences. Let's explore step by step. To understand the end, we must first understand the beginning. Our universe, in all its vast and silent grandeur, operates according to a set of fundamental rules. These are not laws written in a book or decrees handed down by some cosmic authority. They are something far more profound. They are woven into the very fabric of space and time itself, inseparable from the existence of everything we see and know. Scientists call these foundational rules the physical constants. Think of them as the source code of reality, the unchangeable settings in a cosmic simulation. They determine the precise strength of gravity, the ultimate speed limit of light, the charge of an electron, and the intricate dance of particles within an atom. These numbers were imprinted onto our universe in the first fiery moments of the Big Bang, and for 13.8 billion years, they have remained exquisitely, perfectly, the same. They are the bedrock upon which everything else is built. Constant, unchanging, absolute, or so we thought. Now, it's crucial to distinguish these constants from the units we use to measure them. A meter, a second, a kilogram. These are human inventions. Arbitrary scales we created for convenience. The constants themselves are the real objective properties of the universe. They are the same whether you measure them in miles per hour or parsecs per millennium. They are the universe's language, and we are only just beginning to learn the grammar. Let's name a few of these cosmic rule makers. The most famous is c, the speed of light in a vacuum. It's not just the speed of light, it's the speed of causality itself, the ultimate speed limit for any information or interaction in the cosmos. Nothing can travel faster. It links space and time and underpins Einstein's iconic equation, E=mc2, revealing the immense energy locked within matter. Then there is the gravitational constant, g. This number dictates the strength of the universe's most familiar force. It is g that determines how powerfully two masses pull on each other. It is astonishingly weak compared to other forces, yet it commands the grandest scales, holding galaxies together, keeping planets tethered to their stars, and anchoring you to the Earth right now. And there's the fine structure constant, known as alpha. This elegant number is a measure of the strength of the electromagnetic force. It governs how charged particles like electrons and protons interact. It dictates the size of atoms, how they bond to form molecules, and how they interact with light. In essence, alpha is the master architect of all chemistry, and by extension, all of biology. Our journey to uncover these numbers has been a multi-generational epic of human curiosity. It began with early astronomers charting the heavens, trying to decipher the celestial clockwork. It progressed through centuries of meticulous laboratory experiments, and today, it continues at the frontiers of science, in colossal particle colliders that recreate the conditions of the early universe, and with telescopes that peer back to the dawn of time. Each discovery has refined our understanding, revealing a universe governed by a handful of seemingly random, yet incredibly precise, values. These constants are the four fundamental forces of nature. We've touched on gravity and electromagnetism. The other two operate on the subatomic scale but are no less critical. First, we have the strong nuclear force, the heavyweight champion of the forces. Acting only across the infinitesimal distances within an atomic nucleus, it is the cosmic superglue that binds protons and neutrons together. Protons, being positively charged, despise each other. The electromagnetic force tries to push them apart with incredible violence. Without the strong force, which is over 100 times more powerful at these tiny scales, every atom in the universe heavier than hydrogen would instantly disintegrate. No stars, no planets, no life. Just a thin, boring soup of elementary particles. Finally, there is the weak nuclear force. As its name suggests, it is feeble, but it plays a unique and vital role. The weak force is the only force that can change the flavor of a particle, for instance, turning a neutron into a proton. This process, known as radioactive decay, is fundamental. It is the engine that powers our sun, allowing it to fuse hydrogen into helium and shine for billions of years. It also creates heavier elements inside stars, the very elements that make up our world: gravity, electromagnetism, the strong force, and the weak force. Their strengths are defined by these unblinking numbers. For our entire existence, we have taken them for granted, assuming them to be as immutable as the past. But what if they weren't? What if we could reach into the control panel of the universe and just nudge one of the dials? That is the journey we are about to take. We will see how a tiny change in one of these fundamental constants doesn't just alter a few equations. It unravels the very possibility of existence. Our first scenario begins deep inside the atom, at the very heart of matter. To understand the delicate balance that allows our universe to exist, we must first journey into a realm governed by forces of unimaginable power. Here, in the nucleus, the rules of reality are written, and we are about to change one of them. We are going to increase the strength of the strong nuclear force by just 1%. It sounds like a tiny, almost insignificant adjustment, a rounding error in the grand cosmic equation. But this single constant is one of the four fundamental forces of nature, and its value is precisely what it needs to be. What happens when we nudge it, ever so slightly? Remember, this is the force that acts like a cosmic superglue, holding the nucleus of every atom together. It is by far the most powerful force in the universe, but it operates over incredibly short distances, only within the confines of an atomic nucleus. Its primary job is to overcome the immense electrostatic repulsion between positively charged protons. It binds these protons, which desperately want to push each other apart, into a stable, compact core. Without the strong force, every atom more complex than hydrogen would instantly disintegrate. There would be no periodic table, no chemistry, no life. It is the architect of all the matter we see and are made of. So, you might think that making this glue stronger would be a good thing. A more robust, more stable universe perhaps, more tightly bound atoms, stronger matter. It's an intuitive assumption, but the universe is not so simple. Its stability is a paradox, a balancing act on the edge of a knife. And by making this force stronger, we don't reinforce the universe, we shatter it. Because with this 1% increase, a bizarre and catastrophic process becomes possible. Two protons can now stick together much more easily than before. In our universe, if two protons meet, they almost immediately fly apart. The strong force isn't quite powerful enough to overcome their repulsion and bind them. The resulting particle, called a diproton, is fundamentally unstable and falls apart in less than a trillionth of a second. But with 1% stronger glue, the diproton becomes stable. This isn't just a minor tweak to a rare particle. The creation of a stable diproton is a universe-breaking event. It's like discovering a secret shortcut in the laws of physics, a shortcut that bypasses the most important bottleneck in all of cosmology. This single change completely rewrites the rules of nuclear physics from the ground up. The entire process of how stars live and die is about to be catastrophically altered. To understand why, we need to look inside a star like our sun. The sun and other stars fuse hydrogen into helium through a careful, step-by-step process called the proton-proton chain. This process has a crucial bottleneck, a deliberately slow first step. Because the diproton is unstable, two protons can't just stick together. One of them must transform into a neutron at the exact moment of collision, an incredibly rare event governed by the weak nuclear force. This bottleneck is the universe's built-in safety valve. It throttles the rate of fusion, forcing stars to burn their fuel slowly and steadily over billions of years. If the diproton stabilizes, that bottleneck vanishes. The safety valve is gone. Protons can now fuse directly and easily. The slow, patient process of stellar fusion goes into overdrive. The careful, life-giving burn of a star becomes an uncontrollable, explosive detonation. With stable diprotons, hydrogen, the fundamental fuel of the cosmos, fuses at a runaway rate. Any place where hydrogen is dense enough, like the core of a star, becomes a cosmic bomb. The fusion reaction is no longer self-regulating, it's explosive, Stars that were meant to burn for eons, nurturing planets and life, instead flash brilliantly for a fleeting moment, then burn out. They would consume all their hydrogen fuel in a cosmological instant, perhaps just a few million years instead of billions. The consequences would begin just moments after the Big Bang. The primordial hydrogen that filled the early universe would not have waited for stars to form. It would have fused almost entirely into helium during the universe's first few minutes. There would be no hydrogen left for long-lived stars, no fuel for the future, and without hydrogen, there is no water. The simple, elegant molecule of H2O, the basis for all life, as we know it, could never form. The oceans of Earth, the ice of comets, the clouds of Jupiter, none of it would exist. In this universe, life, planets, and even the patient, steady burning of stars would be impossible. The cosmos would be a dark, desolate place, filled with helium and heavier elements, but devoid of the main ingredient for complexity and time. A 1% change, a seemingly trivial adjustment to a single number, led to a universe without a future. A universe that was over almost as soon as it began. This demonstrates the terrifying fragility of our existence, but the strong force is just one dial on the cosmic control panel. What happens if we turn another? What if we weaken the force that holds molecules, and even you, together? Let's reset the universe and try a different glitch. We will leave the strong force alone and make the electromagnetic force just 1% weaker. Electromagnetism governs electron orbits, the basis of all chemistry. With weaker pull, electrons orbit farther away. Every atom becomes larger, and more importantly, molecular bonds weaken. Like building with weak magnets, everything falls apart at the slightest disturbance. Consider water. The HO bonds would be weaker, changing its properties. Boiling lower, freezing higher. Complex molecules, DNA, proteins, cell membranes, become too fragile. Biochemistry grinds to a halt. The world would literally start to fall apart. Solids lose rigidity, reactions fail. Even nitrogen and oxygen could dissociate. Life requires strong yet flexible bonds. A 1% weaker electromagnetic force erases complexity, leaving a soup of simple, disconnected atoms. Now for our third experiment. We will not alter a force this time. Instead, we change a particle mass. In our universe, a free neutron is slightly heavier than a proton and decays in about 15 minutes. Now flip it. Imagine the proton is 1% heavier than the neutron. The proton becomes unstable and decays into a neutron, a positron, and a neutrino. This destroys hydrogen, a proton plus an electron. Without stable hydrogen, stars cannot form or last. All water breaks down. If nuclear protons decay, every element becomes radioactive. Stable elements vanish. Every atom would constantly decay. A radioactive wasteland. A 1% mass change wouldn't just stop stars, it would dissolve the atoms they're made of. Let's reset the universe one more time. The forces and masses are back to normal. This time we adjust gravity, the gentle giant. It's incredibly weak compared to other forces, but its reach is effectively infinite. It governs orbits, shapes galaxies, and triggers starbirth. We're going to make gravity just 1% stronger. Stars live in a delicate balance, fusion pressure pushing out, gravity pulling in, hydrostatic equilibrium. Increase gravity and that balance tips. The core compresses, pressure and temperature rise, and fusion runs faster. Stars burn fuel far faster. Our sun's 10 billion year life could fade in under 1 billion. The cosmos shifts to short-lived blue stars. Few stable yellow suns remain. Cosmic timescales compress. Stars born, burn furiously, and die in a blink. Planets don't cool in time. Complex chemistry stalls. Life struggles to emerge. The universe becomes frantic and fast-paced, without the patience for planets' biology and consciousness. Let's stay with 1% stronger gravity, but, zoom in on our solar system. The sun's entire character would change. Burning hotter and brighter, it becomes bluer and emits far more UV and X-rays. This intense radiation overwhelms magnetic fields and ozone, stripping atmospheres and sterilizing surfaces. The habitable zone moves much farther out. Earth would be scorched. Our oceans boil into space, leaving a desolate, baked world. Survival would require orbits near today's asteroid belt. Even Jupiter's distance. But with a shorter solar lifespan, there isn't time for life to evolve. Our sun would die before intelligence could arise. Earth becomes a frozen cinder orbiting a dead star. Even in a shifted habitable zone, life could never win the race. The stellar clock ticks too fast. Let's zoom out to galaxies, vast spinning islands of stars, gas, and dust. Our universe is rich with spirals like our Milky Way. Galaxies form from a delicate interplay between gravity and the Big Bang's outward momentum. With gravity 1% stronger, density, seeds, grow faster, favoring smaller, denser, more chaotic galaxies. Stars crowd together, violent interactions rise. Solar systems are disrupted, planets flung to the dark or into their suns. Stable systems become rare. On larger scales, everything binds tighter. Expansion could be overcome earlier, even reversed into recollapse. A 1% stronger gravity doesn't just change stars and planets, it rewrites the history and destiny of the cosmos. Small changes can prevent stars from forming, dissolve atoms, and make planets uninhabitable. Life is not a separate miracle, it is a product of physics, complex chemistry exploiting specific elements and forces. Change the physics and you change biology. A 1% glitch makes life impossible. Slightly stronger strong force, hydrogen eliminated. Slightly heavier proton, all matter radioactive. Slightly weaker electromagnetism, molecular bonds fail. Slightly stronger gravity. Short-lived violent stars. Life's chemistry is finely tuned. Carbon's 4 bonds build complexity. Water dissolves and transports. Ice floats, protecting life in winter. Change these constants by 1% and carbon and water lose their life-giving properties. Life's existence is delicate and improbable. Our universe is bio-friendly down to the numbers, from long-lived stars to protein folding. It is all connected. We have journeyed through a gallery of cosmic endings, each born from the tiniest, most imperceptible of tweaks. We've seen how a universe can be unwritten by a change as small as 1%, a nudge to the strong force, and stars burn out in a flash, their life-giving light extinguished before it can ever nurture complexity. A slight weakening of electromagnetism, and the very bonds that hold molecules together dissolve into nothingness, rendering chemistry, and thus life, impossible. We witnessed a universe where a single subatomic particle, the proton, becomes infinitesimally heavier, triggering a cascade of decay that erases hydrogen, the fundamental building block of stars, water, and everything we know. We saw gravity, the gentle sculptor of galaxies, turn into a ruthless crusher, forging a cosmos of violent, short-lived stars and chaotic planetary systems where stability is a fleeting dream. Yet, against all these catastrophic possibilities, our universe stands in stark, beautiful contrast. It is a cosmos of long-lived, stable stars that burn for billions of years, providing the steady energy needed for planets to form and for life to evolve. It is a universe with stable planets in gentle orbits, worlds where the laws of chemistry are robust enough to construct the intricate self-replicating machinery of life. Here, atoms are stable, water is abundant. The dance of existence, from the formation of galaxies to the firing of a neuron in your brain, proceeds with an almost impossible grace. Our reality is balanced on a razor's edge, a sliver of cosmic parameter space where complexity is not only possible, but seemingly encouraged. This brings us to the most profound and unsettling question of all. Why? Why do the fundamental constants of nature have these specific, life-permitting values? It's not just 1 or 2 numbers, but a whole suite of them, each tuned to a breathtaking degree of precision. Why is the strength of gravity exactly what it is, and not a fraction stronger? Why is the mass of the electron so perfectly calibrated against the mass of the proton? Why this specific recipe for reality? Why a universe so perfectly tuned for complexity, for consciousness, and ultimately, for us? Is our existence merely the result of a cosmic lottery? This is the idea behind the multiverse. Perhaps our universe is just one of an infinite, or at least unimaginably vast, ensemble of universes. In this cosmic landscape, every possible combination of physical laws and constants is realized somewhere. The vast majority of these universes would be sterile, chaotic, and utterly devoid of life, flashing into existence and dying in an instant, or expanding into a cold, empty nothingness. By this logic, we simply find ourselves in one of the rare universes where the conditions are right for our existence, because we couldn't possibly exist anywhere else to observe it. It's a form of cosmic natural selection. We won the lottery, not because we are special, but because there were enough tickets to guarantee a winner. Or, is there another, perhaps more elegant explanation? Perhaps the values of these constants are not random at all. Maybe there is a deeper, more fundamental principle at play. A unified physical law. a theory of everything that dictates these values with mathematical necessity. In this view, the constants couldn't be any different. Just as the ratio of a circle's circumference to its diameter must be pi, perhaps the strength of the electromagnetic force must be precisely what it is due to some undiscovered fundamental truth about the geometry of space-time or the nature of reality itself. If such a theory exists, it would mean our universe is not one of many possibilities, but the only possibility. The fine-tuning would not be a lucky accident, but an inevitable consequence of the universe's fundamental logic. This is not just a philosophical debate. It is one of the greatest driving quests in modern science. From the colossal particle colliders buried deep underground to the space telescopes peering into the dawn of time, scientists worldwide are searching for clues. They are hunting for this ultimate theory, this key to the cosmic code. Finding it would represent the absolute pinnacle of human curiosity, a moment when we finally read the instruction manual of our own reality. Whether our universe is a lucky draw or a logical necessity, the result is the same, a cosmos of profound and beautiful connection. The very same laws that paint the majestic arms of a spiral galaxy also assemble the atoms that form your hand. The nuclear reactions that power the sun are governed by the same forces that allow the neurons in your brain to communicate. Everything is connected by this delicate, finely tuned set of rules. The light from a distant star that you see in the night sky has traveled for millions of years, its path dictated by those same immutable rules across the unfathomable void. Our existence, our consciousness, our ability to even ask these questions is a gift of this exquisitely balanced cosmos. We are the universe made aware, and perhaps the greatest adventure of all is not just to exist within it, but to never stop asking why it is so.